Okay, you can start now. It's already 7:03. Let me share the screen. Is the screen visible to us? Am I
Yes, ma'am.
audible to you?
Yes, ma'am.
Yeah, okay. So, welcome to our course Operations Research. Yeah, myself, Jayana Gatri, a teaching assistant to this course. In this week, our content is related to multi-objective programming problem and dynamic programming problem, transportation problem, and assignment problem, right? So, coming to assignment related problem, just see that problem first. Here we had a question that in a multi-objective programming problem, we had two objectives F1 and F2, and there are subjective constraints. So that our requirement is to find the extreme points of the given problem. So, what is the basics for multi-objective programming problem? Generally, you have only a single objective, and corresponding to that, you had a subjective constraints. But in multi-objective programming problem, we had more than one objective function, and all that objective functions can satisfied by this subject to the constraints. And here they had asked that find out the extreme points of the given problem. Anyhow, if the objective functions are more than one, we have a subjective constraints here. So that we can solve this problem by using a graphical solution or simplex method. We can find out the solution of decision variables x1 and x2. But to find out the extreme points, by using the graphical method, we can find out the feasible region. And that corresponding points can be the extreme points. So first, do the graphical method. To do the graphical method, what we have to do first? First, we have to change the subjective constraints to the equations. Here we had x1 plus x2 less than or equal to 5, so I am changing it into the equation. It is the first equation. And x1 plus 2x2 is equal to 2, this is second. And 2x1 minus x2 is equal to 4. Third. Next thing, we have to find out the x1 and x2 points from each of the equation, that while considering for the first, considering x1 is equal to 0, then x2 value is 5. And for the second case, just consider x2 as 0, then find out x1, that is 5. And in a similar way, for the second equation, we can find out the points here, that x1 equal to 0, then x2 is equal to 1, and x2 0, then x1 is 2. Similarly, for the third equation, x1 0, x2 minus 4, and x2 0, x1 1. Uh, uh, sorry, 2, right? 2, x1 2 and x2 0, right? These points we can get from the given inequalities. So next we have to draw these in a graph. Um, Suppose you can see here, this is for x1. This is, basic graphical solution, graphical method x2. So for the first case, you can observe that x1 is 0 and x2 is 5. So the point is locating here. Next, x1 is 5, x2 is 0. The point is located here. Then we can draw the line. And here for the first inequality, we can see that the inequality is less than or equal to 10. Then we have to shade away from the region, or towards the origin. This is like a revision of your basic.
Towards origin, ma'am.
So here it is a less than or equal to sign, so that we need to sign graph it towards the origin. So in this way you can see for the first. And then for the second case we had a points x1 0 and x2 1 here, and x1 2 x2 0, here it is. So the graph looks like, and we have this is greater than or equal to sign, so we can shade the region away from the origin. We can shade it, so that region can be in this way. And for the third case, we can identify the points are x1 0 and x2 is -4. Okay, then we just leave it this, because in graphical method we only do with the first quadrant only. And another point is x1 2 x2 0. So if we draw this point and here it is 0 or -4, somewhere here it can be located. So just take this line, here you can see, and this inequality is less than or equal to sign, so that you can shade it towards the origin. Here you can observe that towards the origin means in this way. So the combined region, you can identify that this would be the combined region. Why? Because here it is in the upperwards, so we can identify all these are the combined region. So here we can find out the points that here it is a 2 comma 0. Just let it by a. What it is x1 2 x2 0. Here how this point can be get? This point can be get by solving this inequality, that equation and this equation. For the first, this line corresponds to the first equation. That is x1 plus x2 is equal to 5, and this line corresponds to the third equation. 2x1 minus x2 is equal to 4. Then you can identify 3x1 is equal to 9, x1 equal to 3. So if you substitute that in x1 plus x2 is equal to 5, then we can get x2 is equal to 2. So this point you can say that B, if we denote it, x1 3, x2 2. And this is the point of x1 0, x2 5, C. And here it is the D. That is x1 0, x2 1. So what are the values we got? Extreme point of the feasible region 2 0, 3 2, C is 0 5, and D is 0 1. So which option is correct? These are the extreme points of the feasible region, right? In the multi-objective programming problem also, that can be the extreme point. So here you can identify the 2 0, 3 2, 0 5, and 0 1. So first option is correct. Is it okay? And next question is that find out all of its attainable solutions. What are the attainable solutions to the given problem? So attainable solutions are, here we had a extreme point. So at each extreme point, you needed to find out the optimal solution. Then we can get an attainable solution. The attainable solution is, out of all the points, we can get an solution, feasible solutions. Out of this, which can minimize it. Here our objective function is minimum. So which solution can minimize? That would be the optimal solution. Right. Here you can observe that the points are a 2 0, 3 2, 0 5, 0 1. 0 1, right, or 1 0 0. So at each of these points, we can find out the objective function values. Uh, our objective function is f1 is equal to minus of 2x1 plus x2. f1 is equal to minus of 2x1 plus x2, and f2 is equal to minus of x1 plus 2x2. So here we had an x1, x2 as 2 and 0. So if you substitute these in f1, can get an objective function value. That is 2 to 4 minus 4 here. At the point of B, 6 plus 2, 8 minus 8 and minus 5, and here it is minus 1, right? And this is only for the objective function f1. We had another objective function f2. Then solve the value of f2 at each of these points. Minus x1 plus 2x2. So this is minus 2, and here it is 4 plus 3, 7 minus 7, and minus 10 minus 2, right? So to find what is an attainable solution from out of these, we can find an optimal solution at minimum of f1 or f2, right? So out of these points, the minimum is attained at minus 8 here from the f1, and here you can say that the most negative value is minus 10, so here the minimum value can attain. So for the f1 objective function, the attainable solution is minus 8, and that is obtained at the point B, that is 3 comma 2. So for the first option and third, we can obtain this. And similarly, f2 had a solution, attainable solution at minus 10. I mean minus 10 solution is, and this is attained at 0 comma 5. So for the first option is right, we can say that. Okay, here we had find out the attainable solutions. These are all we know. But here these are the two objective functions other than the one. Now, what is an efficient solution here? With the same problem, what is an efficient solution and what is an ideal solution? Here is another question. Here up to the attainable solution, is there any doubt?
No, ma'am.
Okay, then coming to an efficient solution, is it feasible? So in an multi-objective programming problem, we can say that the efficient solution is one, that corresponding that is, you can say that is an x naught solution. Then the corresponding objective functions are more. For the first, the solution is obtained where that solution is, objective function solution is not less than, that means there is no other feasible solution of x such that one objective function is less, value of the feasible solution of x is less than the uh, x naught, I mean another. If we had a two solutions like at a and at b, we can obtain the solution of the objective functions, right? So here you can obtain that b is corresponding to x2 x naught, then a c d all are x's, x, v is x naught. Then if the f of b attained at the point b, f of b, here no other solution, sorry, f of x, no, f of x is less, fi of x is less than fi of x naught. Here it is if fi means I am considering only the first objective function. X means I am taking an a, f1 of a is less than f1 of b. It should not be less than f1 of b. Then we can say that is an efficient solution. And also another requirement is this f1 of a is f2 of a is not less than or equal to f2 of b. Here a or c or d you can consider any other, but we can then we can say that the b is an efficient solution. Here you can easily observe that the b is minus 8 corresponding objective function value. This is the only the minimum value corresponding to the other. You can in other way you can say that efficient solution is an unique minimum or maximum corresponding to the our required objective function. So only the unique objective function is there, then a solution is there, then you can say that is an efficient solution. And then what is an ideal solution? If we obtain the solution point, here there are the different solutions. For f1 it is b and for f2 it is c. If we obtain the same solution point for the both, here only two, if we get more number of objective functions, then for all of the objective functions, if we attain a solution at the same point, then that point we can say that an ideal solution. Is it okay? Here it is. Are you understand what is an ideal solution, what is an efficient solution, and attainable solutions and extreme points? That are the four different for multi-objective programming. So is there any queries related to multi-objective programming? I'm moving to the next thing, dynamic programming problem. So what is the dynamic programming problem? Uh, Generally, if we have a large problem, that means it includes n number of decision variables, then the dynamic programming problem divides that large problem into a small sub-problem. And each subproblem has only one variable or a few number of variables, so that at each subproblem or at each stage we can find out the optimal solution, and then integrating that optimal solution we can find out the final optimal solution. And in that division case, I mean subdividing the given problem into small subparts, there is a question that even though we are subdividing the large problem into the small problem, and each subproblem is solving and find out the optimality, then the question is there the one variable in the one stage is dependent to the other stages variables or not? That is the question raised. That question can be answered by Richard Bellman's principle, that states that the optimum policy has a property that whatever the initial state or initial decisions are, but the remaining decisions must be constituted to an optimal policy regarding to the state resulting from the first decision only. So I guess it is a B. Whatever the initial state and initial decisions are, but the remaining decisions must constitute an optimal policy with regard to the state starting from the resulting from the, sorry, it is D, resulting from the first decision. Is this okay? That means in a you had a sub problem of x1 plus x2 plus x3. That means you had three variables either in constraints or in objective function. This function we had. So for the first stage we can subdivide it only x1, and for the second stage we are subdividing it x1 plus x2, and for the last stage we are subdividing x1 plus x2 plus x3. That means we are depending on the solution of first stage's decision. If the optimality of the first initial state or initial decision is whatever, but the remaining decisions all must be depends on the resulting from the first stage decision only. That is stated by the Richard Bellman's principle. Okay, then coming to the next topic, that is a transportation problem. We had seen in the first week or second week, I was not remember that, I had seen the general definition of the transportation problem. That is, the transportation problem has a number of supplies and number of demand, so that the total supply is equal to the total demand, and the total cost has to be minimized from one transportation to another transportation. That can be explained by the transportation problem. And in this transportation problem, we can solve this transportation problem by there are the two ways of solving this transportation problem. One way is to find only the initial basic feasible solution, and other thing is to find the optimal solution. Transportation problem is also a kind of linear programming problem, right? Because we had the cost coefficient Cij and decision variables are the quantities transported from one origin to one destination, that is Xij, and corresponding cost Cij. Then objective function is total Cij and Xij. That means to minimize the cost minimum. This can be the objective function. So these all comes into the transportation problem. So it is also a kind of linear programming problem because it is in linear form of decision variables, that means xij, and also in cost. It is a linear programming problem. So now in a linear programming problem, we can solve the optimal solution by using the simplex method or big M method or two-way simplex method or like that. But here with this transportation problem, they are the methods to find only initial basic feasible solution are northwest corner rule and Vogel's approximation method, least cost method. All these three are comes into find out the initial basic solutions for the transportation problem. And to find the optimal solution, there is a method called MODI, that is modified distribution method. It is to find out the optimal solution. Before finding the optimal solution, first we need to find the initial basic feasible solution. Then only you can find out the optimal solution. So for that finding methods, they are the northwest corner rule and Vogel's approximation method, least cost increment. So here the question that which of the following is not a method to obtain the initial basic feasible solution of the transportation problem. Obviously, you can say bigger method. It is a general basic linear programming problem solving method, not the solution method to find the transportation problem. And just read about this question. You can solve it now. It is a kind of transportation problem. You can observe that here the supply and demand here there, and we can also identify the total supply and total demand is equal or not. If it is equal, then only the feasible solution can be attained to the transportation problem. If it is not equal, then we need to add one more row or column so that the total supply and demand should be equal. That means balanced one. Here the total demand is 22, right? And that the total supply is equal to 22 or not. Yes. So we can get the initial feasible solution. Feasible solution can exist when summation ai is equal to summation bj. That means bj's are the demands and ai's are the supply. Okay. Now the question is to find the initial basic feasible solution using the northwest corner rule and least cost entry method. Okay, first we solve this problem by northwest corner rule, um, where I can rewrite the question that wheat produced at they are the different cities they had given, and also the different can denote it by first. B filler HN, and also they had given the demand 4174. This is for the state Delhi. Can denote it by Delhi D, and which is for Mumbai, and then channel 37426. You try to solve first, and I just explain again. It is the supply. So for the first step is in the northwest corner rule is first you have to identify the left topmost element. Here the first element, that is one element, is the leftmost top element. Then uh, again we need to see that to allot the quantity that is transported, these are the cost, and now we have to find out the quantity that is transported from B to B is transported to Delhi. What is the quantity that? So to find out that, first you need to see which of the which one is minimum, that is supply or demand corresponding to that one element. Here you can identify, you can easily see that the supply 4 is minimum, then 8 corresponding demand. So just cross it out the minimum. Here these are AIs and these are BJs. Then find out the minimum of AI and BJ. That would be the XI. That is here. It is a cost. 4 is the cost. So here you just assign 4. I just okay write it here. 4. Here the corresponding quantity is 4. I cross it here from the supply. Then just subtract the demand by the corresponding supply. So here it is 8 minus 4. You can obtain here 4 only. Cross it out. So next, just eliminate the, here you had assigned the value corresponding to A. That means corresponding to the row values. So that you have to cross out that row. Just eliminate that row or don't mind that row. If the minimum is from the column, then cross it out the column. And next you can see, coming to the next matrix, again you have to see the leftmost corner, that is the north side corner, and identify here it is the one, and identify that corresponding supply AIs and BJs. Here the minimum of AI and BJ is BJ minimum. So here just cross it out. So assign the 4 here, 4 here, and you can see that after eliminating the 4, here also you can obtain that 7 minus 4 is equal to 3, and here it is corresponding to the column. So leave it out that column. I am eliminating this column also, and then from the next step, what is an element? 4, which is the leftmost element in our observation. So for the 4, corresponding A and BJ minimum is AI. So cross it out 3 and assign 3 here. and cross it out 4. 4 minus 3 is 1. Here the demand is 1 only now. It is corresponding to the row, so that now again eliminate this row. And next again 2 is an element. Here the minimum is 1 corresponding to the column, so that here we can obtain only 8. Here assign 1. Again eliminate this row. Why? Because here the minimum we are assigned from BJ. Next 4 is the element. So corresponding minimum is 8 or 6. 6 is minimum, so cross it out and assign it here and subtract it from here. Okay, so 8 minus 6, 2. And again it is corresponding to the row, sorry, column, so cross it out this column. Again we had only 2 cross 2 matrix, and identify here the our desired element is 7. Identify the minimum of A and Bj. Here minimum is Bj, that is 1. Assign that 1 here. So here it is 1, and cross it out the corresponding column because it is from Bj. Next our element is again this 7. So corresponding minimum is attained at from the row, that is 1. So assign 1 here. Here it is 3 minus 1, 2. Uh, then cross out that row. Finally we had only one element. So row and column A and Bj are same. So we can assign 2 anywhere. So we can find finally we had this solution. So this can be identified as 4, 7, 3, 8, 2. 1473. Okay, can easily say. So finally what we had get for the cost in the first row for the cost 4 we had a quantity of 4, and plus for the second row we had for the cost 1 we had the quantity 4 plus 4 into 3. If we multiply all the cost coefficients and the quantities, I mean xij's, then we can get the solution. 6 into 4 plus 7 into 1 plus 7 into 1 plus 2 into 7. We can find out this, can get the solution from the northwest corner. Then least cost entry method will see. And in this, is there any doubts? This is what initial basic feasible solution after finding this. What's the solution here? Is anyone alive?
I'm getting 86, ma'am.
Okay. Is there any doubts from the northwest corner rule?
No, ma'am.
So this is only the initial basic feasible solution. Next is also coming to the another method, that is the least cost entry method. We can see least cost entry method for the same problem. What are the steps involved in least cost entry method? Just rewind first. Okay. Coming to the least cost entry method, first step is to identify the minimum element of the entire matrix. Here, if we observe that from the entire matrix, 1 is the minimum. After finding this minimum element, just check it the corresponding AIs and BJ, which is the minimum. Now, this is the basic cell, 1 is corresponding 1, and identify which is minimum AI or BJ. Here you can identify 7 is minimum, so assign that 7 here corresponding to 1, and just subtract 7 from 8, then we can get 1 here. And then after that we just remove that corresponding row or column. Here we are eliminating the row. Why? Because we are assigned 7 here. So 7 is corresponding to row, so just eliminate it. Then next we have to find out the next most minimum value. Next minimum value is 2. This 2 is corresponding to first row, third. You can identify in first row, third row, and just a minute. First row, third row, and fourth row. Okay, here it is 2. So in 3 different rows, we can identify the minimum value, that is 2. So which one you can select is randomly. You can select any of the cell. Here I am selecting the first row corresponding cell. So here you can see the again the next step is to see the minimum of A and Bj. Here minimum is 2, so I am assigning 2 here and crossing out here and subtracting from the AI. Here it is corresponding to the column, so again cross it out the column. Next, our matrix is only belongs to this first row, third row, and fourth row, not the last column. And next, again, find out the next most minimum value. That is, you can identify again next 2 here. If you see here 2, the minimum value is 4, so cross it out and assign it here, and cross it from here. Here you can obtain 5. So it is corresponding to the column. Then again, cross the column and find out the next most minimum value. Again we had another 2 here. You can observe that 2 and 6 AI and BJ minimum is 2, so assign the 2 value here and cross it out 4. 6 minus 2, 4. So this is corresponding to the row, so that eliminate that row. Here this row is not in our list. So next, from the uncovered values, remaining values, the minimum value is 3, right, which is corresponding to 1, 3, first row and third column. So for these 3, corresponding AI is 2 and BJ is 4. Minimum is 2, then cross it out and assign 2 here, then here 2, which is corresponding to the row. So just cross it out. And the remaining values are 7, 4, and 7. So minimum is 4, you can see here that minimum value 4 and corresponding bj value is minimum, and assigning here, and this is corresponds to the column, so again I'm crossing out this column. Next, values we had, remaining values are 7 and 7, so I can consider any of the 7 value. I am considering 1, so that I am observing that here 1 is minimum, so here it is 2, so it is 1 corresponding to the column entry it is. So I am crossing out. So again the last value is 7, so here it is minimum value is 1 and 1. I am assigning it here and crossing out. So finally you can get the solution as 1 into 7 plus, oh, okay, from the first row we can start. 2 into 3 plus 2 into 2 plus 1 into 7 plus, I mean, why we are doing like this, multiplying and adding the cost and cost coefficients and quantities for 1 into 7. Is Is there anyone can tell why we are doing like this to find the initial basic feasible solution?
Ma'am, these costs are for 1 unit, ma'am, and we have allotted or 3 unit, 1 unit. So we have to multiply by that number, no? So
Yeah.
that we can do.
Mathematically, how we can say.
Cij multiplied by xij. That
So our objective is the summation Cij and Xij. So that's why we are doing like this, summing and multiplying. Okay, is there any doubts from the least cost entry method? So find out that solution. Then from the given question is just a minute. Here it is. For the northwest corner rule, we find out that solution is 86. So only 186. So let's cross check it out. For the least cost entry method, the solution is 54 or not.
ma'am,
Yeah.
we have arbitrarily broken the tie of the two, ma'am.
Yes.
We have allotted. So if I choose some allotted some other two, ma'am, so answer will change, ma'am.
No. Finally, the optimal, I mean, initial basic feasible solution will not change.
Okay, okay, ma'am.
That's why you can choose randomly. Why? Because here you can observe that first I had chosen the first row corresponding to and cross it out. Again, I need to choose here is another 2 and 2. There are more 2's. If any other row or corresponding column is eliminated, then it's fine. If not, then we have to again find out the basic cell also. Right? The
Okay, ma'am.
solution may not change. And here one more thing, that the basic cells here you can count that here it is 1 3 corresponding cell and 1 5 corresponding cell. So finally the number of basic cells we can obtain is m plus n minus 1. M is the number of uh, sorry m okay, m is the number of rows and n is the number of columns. It is rows, n is columns. And we can see that if the number of basic cells finally after getting the solution in any of the method like northwest corner rule, least cost entry method or Vogel's entry method, we can observe that the number of basic cells are m plus n minus 1. If these are equal, basic cells are equal to m plus n minus 1, then only we can say that the feasible solution can attain. This is another way. These are the basic cells. Here you can see hem is 4, n is 5, 4 plus 5 minus 1, 8, right? So you need to get the basic cells as 8, 1, 2, 3, 4, 5, 6, 7, 8, right? And again, you can check it from the northwest corner rule also. Here the basic cells are 1, 2, 3, 4, 5, 6, 7, 8. So number of basic cells is equal to n plus n minus 1 in any method. Okay. Next, going to an another topic, that is an assignment problem. We can say that assignment problem is a special case to the transportation problem. How we can say that in a transportation problem we have the cost coefficient Cij and then corresponding quantities or like decision variables we had an Xij and corresponding supply and demands are Ai's and Bj's. Here you can find Bj's. So in an assignment problem, if the all of the AIs, each of the AI is equal to 1, then we can say in a transportation problem AIs are 1, then we can say that is an assignment problem. And also another criteria that number of rows and number of calls must be equal in an assignment problem. So in a transportation problem, here we identified the rows are 4 and the columns are 5. These are not equal. But assignment problem is a special case to the transformation problem when the number of rows and number of columns are equal, and also the supplies and the demand of each is equal to 1. That means unity only. Ai is equal to 1 and Bj is equal to 1. and number of rows and number of calls must be equal. Then you can say the transportation problem is an assignment problem. So we can say assignment problem is a special case to the transportation problem, special case of transportation problem. And here we can say that our objective function is summation Cij and Xij. And subject to the constraints are in a transportation problem, summation Xij is equal to Ai, total Xij is equal to Ai, and summation Xij, if it is from I is equal to 1 to m, j is equal to 1 to n, then it is Bj. These are the subjective constraints, right, in a transportation problem. So when it is Ai is equal to 1 and Bj is equal to 1, it reduces to the assignment problem. Okay. So in other way, you can say that n columns are the number of jobs and number of persons. Here it is a person jobs. So how many of if we assign a person each person to the each job, then we have to pay them for each job. You have to allocate the person into only one job. Then finally you have to minimize the payment of salary of all the persons. That can be coming into an assignment problem. In that way, you have to assign. Here, coming to the ninth question, in the solution of the finding the solution of assignment problem, the optimal solution is indicated if the minimum number of horizontal and vertical lines which need to be drawn to cover all zeros in the assignment table is. Do you all have an idea about assignment problem or not?
Yes, ma'am.
So tell me that answer.
Ma'am, I think ma'am last option, ma'am, less than the number of jobs, ma'am.
Is it?
Last option, ma'am, less than number of jobs.
Okay, verify that. Okay, I coming to explain the problem, then we can get a solution of this.
Ma'am, this I have done by just ma'am examples, ma'am. I have counted, ma'am. Always it is coming, ma'am, less than number of jobs, the number of lines we are drawing.
But to find out the optimal solution, that would be same as the number of jobs, or you can say number of jobs is the dimension of the matrix. Uh, that means order of the or order of the matrix, right? Because in an assignment problem, number of rows and number of columns should be equal. So same number of jobs means same as the order of the matrix. The draw if the draw lines should be same as the order of the matrix, then only we can go to the finding an optimal solution from the assignment problem. If it is less than or equal to, then we need to do an another iteration or another step to make the number of draw lines equal to number of jobs. Okay. I understand what was your problem. I'll explain through this problem.
Okay, ma'am.
So here is a question. Um, Here, first in an assignment problem, we need to find out first the given problem is in the minimum state or maximum state. Here they had given the question of that the traveling distance is to be minimized. Here there are some pharmaceutical single product of selling five agencies A, B, C, D. You can consider it as five agencies. These five agencies are selling the pharmaceuticals from two different locations like A, B, C, D, G. So that we have to minimize the total traveling distance. These are the traveling distances. So it is in the minimized case. So they are the minimum case, so we can solve easily. If it is in the maximum case, then we have to convert into minimum. How we can convert into minimum, that I'll explain next question. First we can see here it is a minimization type, and they are the four steps. That are first one is row operations, and next is column operation, Third is draw lines, and these draw lines must be equal to the order of the matrix. If it is not equal to, then we have to do an again step. And after finding the draw lines, if the draw lines are equal to the order of the matrix, then do the zero make assignment. Then finally you get the solution, assignment solution. So for our problem 160, you know what is row operation? First step.
Ma'am, subtract the least from
Each
every entry, each row that.
by,
Yes, ma'am.
and in the same way for the columns also you need to do. So these are the given. So first to do the row operations, we need to select the minimum of each row. Here we can identify that 115, 115 is the minimum of the first row, and 120 is the minimum of second row. Here 110 and here 50. We can randomly choose these or these. I'm choosing first, and 35 is the minimum. So first we have selected the minimum of each row. Then row operation is that we need to subtract the remaining all of the elements of that row by that minimum value. Here if we subtract it by 160 by 115, we can find out 45, right? 45, and 130 minus 115, it is 15, and 190 minus 115, it is 75, and 200 minus 115, it is what it is, and do it to the all the rows, all the corresponding rows. I just
Ma'am, after 15 there will be zero, na, ma'am.
after,
15, ma'am. There will be zero, na.
yeah. Okay, okay, here it is 0, 75, and here it is 85. 115 minus 115 is 0. So here 135 minus 120, that is 15 and 0, and 130 minus 120, 10, 40, and here 175 minus 20, 55. Right. In a similar way, you do for the all the rows. Then you can find the row operation. So first step is done. I just write here 0 and 0, 50. So we are done with the row operation. Next thing is to find out the column operation. That is to find out the minimum of each column, and then in the similar way you have to subtract that from the remaining elements of that column. Here in the column you can see that 0 is the minimum, and in this column also 0 minimum, in this column also 0 minimum, here in this column 30 is minimum, and in this column 55 is minimum. So subtract it, subtract other elements of that column by 0 for the first column. Then we can find as it is for the first column and as it is for the second column and third column also as it is and fourth column would be changed. Then draw lines. Here we have to subtract it from 30. So 45. Here we have to subtract it by 55. Then it is 30, 0, 55. Is it so? Next, draw lines means we have to draw the lines that covers the all of the zeros, but need to draw the minimum number of lines that has to cover the zeros, all of the zeros. Here in the first row I had a 0 and I can draw like this. Here there are the four zeros. So first I am covering all these four zeros. I am drawing a one line, and again I am drawing another line here to cover all of these zeros. And here is another zero. Here is another zero, and either row or column we can draw. I am just writing to the corresponding column. So here the number of lines are 1, 2, 3, and 4. But the order of the matrix is 5. Number of draw lines, which is not is equal to the order of the matrix. That is 5. Is this you are finding before one person has said that number of draw lines are less than, always he is finding that less than order of the matrix. Yes, we can sometimes we can find in this way. If we get in this type of draw lines, then the next step we have to do is you need to choose the minimum value from the uncovered elements. Uncovered elements means except the draw lines. What is the uncovered elements? Here it is 45 and here it is 45, 10, 30, 15, 20, 30, 50. All these are uncovered elements. From the uncovered elements we need to find out the minimum value. Here I am observing that 10 is the minimum value. And then we have to subtract the uncovered elements by 10 and add the intersection of the draw lines by 10 and the remaining covered elements should be same. If we do like this, the minimum is 10, so that we need to subtract it from the 10. Here 45 minus 10, 35, 15 minus 10 for the uncovered elements, 5, 20, and here it is 0 is a covered element, so 0 should not be changed, and 20 is uncovered elements, and 20 minus 10, 10. Here 15 is covered element, so it is same, and here this 0 is an intersection of the draw line, so that at this place we need to add by the minimum value, that is 10. 0 plus 10, it is 10, and it is next 0 is only an covered element, so it is same. And in a similar way the covered elements are same and intersection. Yeah, eliminated anything. Oh, here it is only 1 0, right? I don't know what happened to my eraser. Okay, here 0 and uncovered element is 10, that is same, and here is another uncovered element, that is 15 here, and here it is 30. It is an intersection point, so 30 plus 10, it is 45, 40 intersection. and here 45 is same because it is a covered element, and subtract is uncovered element has to be subtract. So 45 minus 10, 35. It is 0, 10 minus 10, 20, 0 and 5. Here it is 30, 30s are same, covered elements are same, and intersection points should be add. Is this step is clear to all? Here it is.
Yes, ma'am.
So in next, again you need to draw the lines. So here to cover the zeros I am drawing again the lines. Here also you can identify these are only the 4 lines, not the 5 again. So again you need to do the same similar step. That means identify the minimum of the uncovered elements. I am identifying it as 5. Then again subtract the uncovered elements by 5 and add at the intersection points, and covered elements are same. After doing that steps we can find out that here it is the 5. So subtract it from the uncovered elements and remaining are same, 15, 0 and 5. Here it is an intersection point, so 0 plus 5, 5, 0, and adding at the intersection point again 15, 0, 0, 15, and here it is 15, 40, sorry here it is 45, add it is 40 is an intersection, so adding. So again here it is 35 minus 5, 30, 0, 15, 0 and 0. uh, 25, 0, here it is 20. So now this is the matrix. Again you need to draw the line covering the all zeros and minimum number of lines to cover all zeros. First I had chosen that, and here two zeros, and these are two zeros, and here is 1 0 and 1 0. So how many of the lines I got? 5 lines, right? So here you can identify the number of rows is equal to number of columns. So our desired matrix is ready. Next thing you need to do is, oh, okay, I go to the next page. What happened? Okay, I am taking this. Oh, I think there is a technical error. Sorry. Okay, I will open a new file. Oh, not copying also. Okay, I make to draw here only. So finally, what we get here, it is 30 in a small. Okay. Finally, we got that 30, 15, 0, 30, 25, and finally 5, 0, 45, 0, and 10. Right. So you need to find out the first zeros, corresponding zeros. You just do the square box. First, I am choosing this zero. Then, if any of the corresponding zeros belongs to the rows or columns, then cross it out. Here, no other row or no other column had zero, so it is okay. And in the second thing, I am choosing, if I choose this 0, then I need to cross it out all these corresponding column zeros and row zeros. So that I need to cross out this 0, and this. In the second row, I had 0 at the fourth position. If it is, if we assume that way, okay, then it is, I am choosing this and crossing out this, crossing out this and this. So here I am crossing out, then it is only the one, and here it is only the one because I am crossing this. Here it is only the one. Then I am crossing this because in this column I am already chosen these zeros, so that we need to cross out remaining zeros corresponding that column and rows. Then we are not finding a solution that in the third row you can identify no assignment of the zeros. So this way of allotment is not good. So instead of that, here we can change to select a 0. Okay, again I show you 15, 0, 30, 25. So if it is this, then for the first time I am choosing this 0, and previously we had a mistake that selecting this 0. So now I am not selecting that 0, selecting last 0, so that the corresponding row zeros are crossed out, columns not had any 0. For the third column I am choosing this 0, only one 0 is there, and corresponding column zeros I am crossing out, so that uh, for the fourth row, if I choose this 0, I can choose this 0 or at the fourth position this 0. If I choose this 0, then I have to cross it out this one and also this one. If I choose this, then I have to cross it out that. Okay, here I am choosing this. Let's see. So that I have to cross it out this. Then the final one is this. How is I cannot choose this 0, right? Because here Okay, I can choose this 0 because I had already crossed out this. So this way of assignment is correct. If I choose this 0, then I need to cross it out last 0, last row 0. Then in the last row, you need not get any assignment. So in that way, you need to carefully see about the assignment at the last step. So here you can observe that A, B, C, D, E, and these are 1, 2, 3, 4, 5 columns. So A assignment is corresponding to, here I am writing it, look it here. A is corresponding to the third, and B is corresponding to the B can assign it to the fifth, and C can be assigned to the second, D can be assigned to the first, and E can be assigned to the fourth. So our assignment problem was done. Our current question is here it is. Okay, these are A, B, C, D. So just find it out. A is 3 means A, B, C. A, C, B, E, C, B. I think first one is correct. And after getting that, we had an assignment that A is corresponding to C, so this is the value, and B is corresponding to E, that means this is the value. So like that we can get all of the values that are the distances. So if we add those all distances, we can get the final optimum traveling distance that should be in the minimization. Is it okay? Any doubts in this?
No, ma'am.
Okay, next thing to cover is if the assignment problem is in minimization type, no, sorry, maximization type, then we need to convert into minimum type, then again do the same, then again do the all these same operations. So how to convert that to maximization into minimum? I can tell you here is another question. It's not visible, but I can tell you in short theory. Uh, if the assignment problem is in the maximization type, then to convert into the minimization type, just subtract it, multiply it, the each element by -1. That is one way. Or we can do another is find out the most minimum value and then subtract it from all other values. Sorry, highest value from the entire table. We need to find out the highest value, not belong to this question, any other question. Find out the highest value of the entire matrix. First select that highest value and then subtract that highest value from all other elements has to be subtracted from that value, highest value. So here we can see that suppose this is the maximization assignment problem. Here 175 is the maximum value. So first we need to select that 175 and subtract the each of the elements from 175. So that means 175 minus 160, 175 minus 130, like that. All of the matrix has to be done in that same way. Then again you can do the in a similar way. Uh, After doing that, it is converted into the minimization type. Then you can go with the given our procedure to find out a solution for assignment problem. And there is an one more thing to you can find that sometimes the values of the corresponding rows or column, any of the corresponding row or column cells can be missing. In that sense, you can take the most positive value. Let us say infinity, that infinity is the most positive value. If in the given problem, if I may not observe the AD corresponding one, if suppose I may not observe this 190 value, I don't know what was the distance from A to D, that I don't know. So that problem may can arise. So in that case, you need to take it has infinity. Then if we subtract it or add it at any time, that would be the infinity only. Then do the same operations. That is the
Ma'am,
necessary. Uh-huh.
ma'am, for any type of problem, maximization or minimization, we have to add infinity, add the missing value, ma'am.
Yeah, in any case, maximum or minimum, just do it with infinity. Why? Because in infinity, if we add or subtract or multiply anything, it would be the infinity, right? So maximum minimization part type is not that much affect.
Okay, ma'am.
Okay, I'm done. Is there any questions relating to today's? I can tell you. Actually, one more problem is there, but this is not working well. But I covered with the theory. Okay, then. Okay, thank you. I'm going to terminate. If you had any doubt, okay, thank you.